functions. So Filipe, it's for you.
Thank you. I hope you are all hearing me well. My name is Filipe Guimaraes. I work currently at the Jülich Supercomputing Center at Forschungszentrum Jülich, and I was formerly at the Peter Grunberg Institute. I worked in the group of Samir Lunis, who could not be here today, unfortunately, presenting about no-equilibrium green function. I hope my talk, it's not the same thing, but I hope it's also interesting and not too basic or not too advanced. But since it's a school, I think it should be fine. So my motivation, this is a talk I gave many years ago, and I didn't have too much time to prepare. I just adapted a few things on these slides. And my motivation actually to work on this started, my talk will be, I'll talk about my motivation, then give some theoretical approach. There will be a lot of calculations here, theoretical derivations. I may skip a few of them, and I will share this slide, so hopefully I put a lot of derivations and hope you can follow that. And at the end, I'll give some applications of this theory that I have myself used in my own work. The bibliography I used for this talk are some interesting books and papers. And as I was saying, my motivation to start working on this was more on the technological side, as many who start working on condensed matter physics. This actually was my old slide that I have here, updated until 2011, and the Moore's law at that time was following a pretty much exponential behavior. The transistor counts doubles every 2 years. This is basically the Moore's law that we all know. I actually found a better figure for that last week, which shows that although the transistor count is still doubling, there are other things that are starting to saturate. For example, because the power was starting to get too high, we could not continue increasing the frequency of the cores of our processors. So instead of increasing the frequency, we start to putting up more logical cores in a microchip. So the transistors continue increasing. But of course, this is possible because the microchip, each cell is decreasing in size for all the years. Again, this was my old slide. I have found that some adaptation. There was actually a delay on 2015 because things are, when you are so small, things are not that easy to manipulate. So the quantum effects start to become very important, and we cannot keep decreasing the size forever to continue doubling the number of transistors. So we need to find alternatives for our technology. The main thing that is important is that anything that we want to manipulate, so we are thinking about the bit in the computer, we want to change the bit or to read the bit, we always need to apply some perturbation. So to see something, to investigate some physical properties of a material, we need to apply some external stimulus to observe it and to see how it's state or to control it. And then we see how it responds. So for example, in this case of STM tip, you can put some atom or some cluster in a surface, then you go with a tip on top of that, then you apply a voltage here, and then you see a signal, which is a current, and then you can draw conclusions from that. Another possibility is that you have a source and a drain where you apply, again, you have a material in the middle, a sample that you have a current passing in this material, and then you measure the conductance of this material, and then you know what is going on. You take some conclusions of how are the states of the sample, and these always involve an application of an external stimulus. So one very pictorial way of drawing this, for example, in a magnetic system, you can apply a magnetic field in this sample. This will determine the equilibrium direction. Sorry if this is too small. So there is a magnetization direction, equilibrium direction, and then you can apply some time-dependent field to make this magnetization process and see how is the dynamics of this system. And then with that you can measure different quantities, and you see how is the intrinsic excitation of this material. For example, this can be put into a cavity, and this cavity is at resonance with a given frequency, and then you change the external magnetic field, and you see that there is a given resonance, a given value of the magnetic field that sets the system into a very big response. So your system responds to that given magnetic field. So this is basically the motivation to study this. And how do we do this theoretically? Of course, everything we do involves some approximation, and this is a linear response approach, where we consider that the applied perturbation is not too big to disturb the system too much. So how do we do this theoretically? By the way, you can interrupt me at any time to make questions. I cannot see the chat here, but yeah, I can answer questions also at the end. So I start with the general thing. I apply some external field. This field can be anything at the moment. It could be a magnetic field, it could be an electric field. And then this field will couple to some quantity of the system, A. So magnetic field will couple to the spins of the system, an electric field will couple to the charge. But then, in general, we can write something like that. An interaction Hamiltonian that is given by the field multiplied by the operator that describes this Hermitian operator that is associated to this quantity A. And currently, at this point, I'm just supposing a scalar field phi, but it could be also a vector field. It just would have 3 components here. So this field is coupled to some quantity A, but then we want to measure another quantity. It could be anything else on the system, B, a quantity B on the system. And if we want to investigate what is the observable B, what would be the measure to what will we measure on B, we just have to do the expectation value of B on a given state of the system. And this state of the system is just an eigenstate of this Hamiltonian. Of course, if this is time independent. And as I said, we will assume here that this field is sufficiently weak that does not perturb too much the system, that we can treat it in just at the linear term on the response. So we have also to assume in this case that when we are at a very long time ago, very before I apply the perturbation, the system, the system should not be perturbed. Otherwise, any perturbation that it could be as small as possible. If you are applying since minus a long time ago, this builds up in the response, and in the end, you have a very large response at time t equals 0, when we are doing some measurement, for example. And then to guarantee that this is not happening, these points are more a mathematical thing. We have to introduce a factor, an exponential factor, that to assure that at t at minus infinity, the perturbation goes to 0. So this these 2 points are better explained in this equation. So our Hamiltonian is not exactly h0 plus h int. We add this exponential with a small eta here, just to make sure that at t equals minus infinity, our Hamiltonian is just the unperturbed one. Okay, so as I said, at t equals minus infinity, we have the unperturbed Hamiltonian, and then we know the eigenstates of this Hamiltonian, because it's just the unperturbed Hamiltonian. We just have h0 with states phi 0 and eigenenergies E0. Now, if we put t equals 0, then the exponential gives 1, and then we have just the Hamiltonian that we want to solve. So at t equals 0, we have h0 plus h int, and then the solution is some phi that we don't know at the moment. This is what we want to solve. Yeah, there are many ways to do this. I'm going to follow the reference I mentioned before. So it is convenient to work then with the interaction picture. And just to remind you about that, if you forgot, in the Schrödinger picture, we have that the state vector has some equation of motion, that they evolve on time, and the operator is not evolving on time. So if the Hamiltonian is independent, we can just have evolution operator here to evolve from t equals 0 to some time t equals t. In the Heisenberg picture, on the other hand, the state is constant. It does not evolve with time, but then the operator evolves in time with the Hamiltonian. And then if the Hamiltonian is time independent, we can have this Heisenberg equation of motion. And finally, in the interaction picture is something in between these two, where we separate the Hamiltonian into two pieces, the h0, which is the unperturbed Hamiltonian, and h int, which is our perturbation, our external field that we are applying in this system. In this case, the equation of motion of the state goes with the h int, and this, yeah, if this is time independent, I would have an evolution operator like that. Otherwise, it's a bit more complicated. And then the equation of motion for the operator is given by a Heisenberg equation, but only with h0, with the unperturbed Hamiltonian, not the full one as I have in the Heisenberg picture. Okay, so going back to our equations here, as I said, at minus infinity, this is our eigenstate. We're supposing we are in the ground state of h0, which is phi 0. Then at t equals 0, we need to evolve this eigenstate from minus infinity to t equals 0. And this will be done by some evolution operator. Now I'm writing it more general here. The evolution operator can be with a time-dependent Hamiltonian. Then it's written in a more complicated form, but we'll still do some approximations on that. And yeah, the state at t equals 0 in the interaction picture is the same as the state in the Schrödinger picture at t equals 0, which is the same as Heisenberg. Okay, then let's go back and remember, what do we want to know? We want to measure some quantity B on the system. What is the observable B? How does it evolve on time? And then we just need to calculate the expectation value. And this is written then in the interaction picture. Just this quantity. Now I'm writing what is this interaction picture vector state with respect to our eigenstates from h0. That's it's at minus infinity. I can write this thing, and then I'm just opening this up. If I go back here, it's an exponential So this exponential, I can just write the series of this exponential. And the first term will be 1 times phi 0 plus the first term, which would be the argument of the exponential, times phi 0. I would have the quadratic terms and so on, but now I'm cutting at the first order because this is the linear response here. I'm just getting the linear term on this response. So our state at a given time t will be the original one plus this change, which I'm calling psi 1. So our quantity that we want to calculate is just expectation value of this, which has 2 terms on each side. I do the product. I have 4 terms, phi 0, phi 0, phi 0, psi 1, psi 1, phi 0, and psi 1, psi 1. And let's assume that we just want to know what is the change caused by the field, right? We have something before, we apply a field, what do we have now? So what is the change that was caused there? This is what we had before, the expectation value with the eigenstates of H0. Then this gives some change caused by the field that are these 3 terms. But of course, this one, psi 1, psi 1, have 2 times h int. So this is a quadratic term, and we are already throwing quadratic terms out here. So we throw away also this second order term. Then in linear response, we have just a simple 2 terms for the change caused in an expectation value of some quantity b. Now we go back to our expression. I just won't go too much into it. You just need to know that this one, psi 1 is on one side, on the second term, psi 1 is on the other side, and this ends up being a commutator between the quantity b and the h1, which is inside psi 1. And, well, this is already an important result, and I'll be using this later. But we can even go further, and let's write in terms of our field that we are applying, the general field phi. When I substitute this back here into this equation, I get just a commutator of b, which is the quantity that I'm measuring, and a, which is the quantity that the field is coupling to. And of course, this integral here, it's from minus infinity to t, because my state is evolving from minus infinity up to time t. But I can use a step function just to write in a more general form, which is basically the full integral on the space integral over time of this quantity times my field. Yeah, we can manipulate this back to go to the Schrödinger picture. I will just skip some details on the mathematical side here and use the fact that phi 0 is an eigenstate of H0 to write this into this form. So we have that the change in the B field into a B quantity, in the observable B, due to a field is proportional to this field in linear response, of course, multiplied by some quantity, which I'm calling chi. This chi is a very, very important quantity, which is, it's written in different forms, chi, or with these double brackets, or even g, because this is called the green function, the double time green function, or susceptibility, or response function, because this is a response to an external field, and this can be written like that. And one thing that is important to mention is that we can identify the quantities that are inside this. Sorry, let me go back here. the quantities that are inside these expectation values, they can be identified as the Heisenberg representation of B, but on the unperturbed system, because what we have inside, if you look at this expression, so this is the relation between the interaction picture, the Schrödinger picture, and the Heisenberg picture. You see that this only involves now H0 and not H int, not the interaction term. So this is basically the Heisenberg operator of the unperturbed system. So everything that is inside chi is only involves the unperturbed system. There is only phi 0 and H0. So this is an important point. Within linear response theory, we are applying a field, and the response of quantity B is given by some response that only involves the unperturbed system. There is nothing about the perturbation inside chi, or inside the response. There is no interaction part here. Only that it's coupling to some quantity A. And these are the known as Kubo formula, because Kubo got this in 1957. So it's quite old. So the way I wrote the expectation value is taking the ground state at t equals 0, but of course you can generalize to finite temperatures using the partitional function, and you have the grand canonical ensemble, grand canonical ensemble, and this response function is quite general. So as I mentioned, these are known as Kubo formula. So I have some remarks just to make, just some points, that the delta function that appears reflects the causality. I'm applying something on the past, and I'm measuring what this is causing at some time t. So the response is a build-up from what happens in the past. But there are general other quantities. There are the retarded function, the advanced Green function, or the causal Green function, that are used in different fields of physics. In this, we only have the retarded one. Of course, we can also work with the advanced one because they are related. All of these are related. And actually, in non-equilibrium Green functions that Samir was supposed to give a class, all these are connected. And here I'm using this notation for the commutator and anti-commutator. And this is also explained. All these different Green functions are very well explained in Zubarev's paper. Okay, so that was just basically the definition of a linear response theory and response functions. Now, what do we do with that? How can we calculate, for example, these response? These response are important to know. For example, how will a given system, I don't know, iron bulk or a multi-layer, how will this system respond when I apply some electric field or some magnetic field? If we manage to calculate this function, we know how the system will respond, and then we can try to find out what would be the ideal system to give some strong response or some weak response. So one way of calculating this is using the equation of motion. And the equation of motion is basically defined if we get the time derivative of this Green function. Here I'm using the double brackets to write the Green function that I defined before. Just to remember, this Green function is just minus I over h bar, the step function, and then the commutator, the expectation value of the commutator of B, the quantity I'm measuring, and A, which is the quantity that the field is coupling to. Then if I get the time derivative, I have two terms which has time dependence here, the delta function and the B. So this generates two terms, and the first is just a delta, the derivative of the step function is the delta, and the second term, the time, this I can write in Heisenberg equation, Heisenberg picture, and dB dt is just the commutator of B with the Hamiltonian H. And then I can build up a higher order response here. And yeah, so this is again just like this response, but now instead of B, I have the commutator of B with the Hamiltonian H. And now if I write the Fourier transform of this equation, the time derivative gives a frequency, the delta is just a constant, and this is the higher order, another green function. I start with BA, now I have commutator of BH with A. Yeah, in general, the second term just produce higher order operators, as I will show very soon. In some of the cases, this is just when we calculate this commutator, the result is just proportional to B, which brings back to this equation, and then we have an exact solution of this. And even when this does not happen, we can decouple this equation by using some approximations to these higher order terms. What do I mean by that? I would just give some example. In the Anderson model, for example, we have an impurity Hamiltonian, which can be written like this. Here I have some states for spin up, some energy for the spin up, energy for spin down, and some interaction. When I have more than one electron, they interact with an energy U. Then I have some free electrons path here, the C operators, and then the coupling between the impurity state and the electrons, and the free electrons. So in this case, if I calculate, for example, this is just one given quantity that we could be interested in. This is just the monoelectronic ring function of the system, is the green function of D and D dagger. Here is just the commutator of the first term, the commutator of D dagger is just 1. Then we have this higher order term, then we have this higher order, which is the commutator of ds with the Hamiltonian, and then dh on this side. So the commutator of d with c does not show up. The commutator of d with d that has in one of these terms, in this one, also doesn't show up because d and d, commutator of dd equals 0. Only d with d dagger is 1. And these are the terms that are left. So, long story short, the commutator of d with this term of the Hamiltonian will be proportional to d itself. So in this case, the green function is not generating a higher order function. This term is just the same as on this side. It will be the same. But I have also this one, which has 4 operators. It's an interaction term. And when I calculate the commutator, it gives back, the result is 3 operators. So I would have here the commutator of 3 operators with, well, the green function of ddd, column, semicolon, with d dagger. And this is a higher order term. But then, sorry, it's here. But then this term can be approximated by getting, for example, this is one possible approximation that we can do, is that here this term is proportional to the n operator, the number of electrons, and then we end up with a number that we can put outside times the d operator. And this again brings back to the same green function as I have on this side. Okay, this is also very mathematical. I will skip a lot of this part. I just want to point out some of very interesting properties of these green functions. First, I can also, I just point you to the fact that the green function, this double time green function, it's double time because we can have 2 times here, but this green function can be written in terms of these correlation functions. What I call correlation function is just the expectation value of two operators at different times. And of course, this can be written as with the partition operator because it's an average. And yeah, I'll just skip some of these properties. I will come back to this later. We can write the step function using this representation with an integral over the frequencies. And it's also interesting to look what happens to the Fourier transform of this green function. So these correlation functions, which is the average that I just show up here, I can write also using the eigenstates of the Hamiltonian. I can put, for example, identity here in the middle, which is the sum of ket bra n, and yeah, the exponential show up. This exponential that is here show up here with a difference of energies because one comes from one side and the other comes from the other side. And I have the 2 correlation functions. I'll just keep, there is it's every step I try to write here, but it's not important for us to follow now. And what is interesting is that I can relate the J, what I call J is the Fourier transform of the correlation function in time. These are correlation functions in frequency domain. And these correlation functions of BA is just an exponential, is proportional to the AB with just an exponential term. And now we just can use this fact to rewrite the green function using all these expressions that I wrote before. I can write the green function, the Fourier transform of the green function with, complicated, but there is an expression for that. And this can, I can write the retarded and advanced. And it's interesting to know that the retarded green functions has poles in the lower half plane, but it's analytic on the upper half plane. And on the other hand, the advanced green function has poles on the upper half plane, but it's analytic on the lower half plane. And with that, we can define a general G of Z, some imaginary frequency, I mean some complex frequency in general, in the complex plane, where I write just instead of omega 1, I put here, instead of omega plus iota or omega minus iota, I just call this Z, which can be anything, complex. And then on the upper half plane, I have the retarded green function, which is analytic. And on the lower half plane, I have the advanced green function, which is also analytic. And they showed, Bogolubov and Parasiuk showed that these are analytic, as I showed before. And now this function, this general function, if I calculate in the upper half plane minus 1 in the lower half plane, this is the difference. It's just some substitution of the expression that I showed before. And now if we do the limit, you see here on this side, I'm calculating on general points, but now if I do the limit where this point in this eta imaginary part goes to 0, they approach the real axis, and we see that this quantity is not 0. There is a branch cut here. There is a value coming from below and a value coming from the bottom. And these values are different. And the difference is basically the correlation function. So there is a relation between these green functions and the correlation function. And it's not a complicated one, actually. Yeah. So I'm just repeating here the retarded green function expression. And I want to show another very important relation. If we get this expression, which is complex, because we have this guy here, and now I use this identity, the limit of this when eta goes to 0 is just some principal part, which is real, plus minus I times delta. Now I have a quantity which is completely real here, minus a quantity which is completely imaginary. So this is the real part of the green function, and this is the imaginary part of the green function. So we can relate these two things. You can notice that J1 plus this expression is already inside the real part. So the real part is related to the imaginary part, can be obtained if you have the imaginary part of the green function, you can plug into this expression and get the real part. And this is known as the Kramers-Kronig relation, which is valid actually for any complex function which is analytic. Okay, so I just showed, these are a couple interesting relations about the green function, that it has a branch cut at the real axis, and this Kramers-Kronig relation. And yeah, I want to show also another, this is actually a very important point later on to understand the meaning of this green function, which is the fluctuation dissipation theorem. So this fluctuation dissipation theorem is just to relate the energies, the absorption or dissipation energies, with the fluctuations of the system. How do we do this? So I will start over. I'm going to simplify a little bit. Just say that my general field that I apply there in the beginning is just harmonic field. It's not a general one. I'm just applying with one given frequency and one given K. But then we can integrate over frequencies and K later if you want. But this is just one given harmonic perturbation. And this field, which is real, can be written, of course, the field that we apply in a lab, it's real. Then we get these exponentials. Now this term that I have in the beginning, instead of having the full integral over R, I can write, I have only these two terms with K and minus K, because this gives is just the Fourier transform in space of the A of R. This gives me A of K and A of minus K, which of course A of K and A of minus K is one is just the complex of the other. So if I get the dagger of this guy, I'll get dagger here and a minus sign, which gives me the minus K. Okay, so now this is my interaction. I will not do what I did with linear response theory. What I want to see now is what are the energies, absorption energies of the system. So first I have to see what are the possible excitations of the system. And for this I will use Fermi's golden rule, which just gives me the rate of excitations from a state I to a state F, an initial state to a final state, and then I'm summing over all the final states. This is just this expectation value squared, and here in the middle what shows up is the interaction, is the V, or the extra term in the Hamiltonian that is causing these excitations. So I'm putting this guy here, and the first term will give rise to this one. And then since it's squared, the field here will show up squared. And these are, of course, the transition energies of the system. I have this omega, it shows up. This is just possible transitions. Now, the second term is basically the same thing, but now with A of minus K. But frequencies are the same with a minus sign. And the total the total transition rate will be the sum of the two, but I don't want only the transition rate, I want the energy absorption during this transition. So I'm multiplying every transition by the energy that it will be absorbed or dissipated on this transition. So the rate of transitions multiplied by the energies gives me the energy rate of this, when I apply some perturbation. So this is the total energy rate absorbed by the system. And, well, because this E minus EF shows up in the delta, or EF minus EI, sorry, shows up in the delta, all of them with this H bar omega, I can just filter this EF minus EI. This will give me the omega that goes outside. And we can also, this is the, just the dt, but now we can calculate the probability of that, some average of that with some partition function. We can write in this form. And here we can compare to what I had written before for the correlation functions, and we can identify this. I will not do this now, but I mentioned here where I wrote this, and just comparing what is I with M and F and so on, we can see that this is basically one correlation function with A minus equals minus K and AK. And in this case, note that this is an expectation value squared. So the one, I can write this as an expectation value times its conjugated, which is giving the A and A minus K. And the same thing on the other side, but now inverted. One is A minus KK, and this guy will be just inverted, AK, A minus K. So this term gives rise to this guy, this term gives rise to this guy, which already simplified a lot our expression for the energy rate. And finally, I'll use this expression that I deduced before just for this part. The relation between these two correlation functions are just the exponential, and we get this this form. Again, we can identify this with the expression I got in this in slide 26, which is basically the imaginary part of the green function. Now I'm writing with chi instead of the double brackets, but it's the same quantity. And we see that the energy rate of a system, the dissipation energy and absorption energy of a given system, is just proportional to the imaginary part of the green function, of this double time green function or susceptibility. So if I calculate this imaginary part of, not only that, actually, I have to note that it's this form of the susceptibility. It's a dagger. If I have some general A-B operator, the imaginary part of A-B, which are unrelated, this is not related to, this is not a energy rate. But if I have susceptibility, which is a dagger, response type, then this gives me the energy dissipation of the system. And I will show an example of that. This probably is a lot of, it's very abstract now, but I will give you an example of that very soon. So, this just shows that the system absorption energy rate is proportional to the imaginary part of the susceptibility, which again only involves unperturbed quantities of the system. So, there's nothing about the perturbation here except what is coupling to the field. Okay, so that was a lot of theory. I hope everyone is awake. I cannot hear you, I cannot see you, and if you have any questions, as I said, just interrupt me, but I don't know how it's there. I'll just continue for now. And I'll just show some of the applications. First of all, I want to make I will not do the full the derivation here. I just want to make a remark because I was very general, and also this class is just I'll probably finish in 1 hour and a little bit, and it's quite all quite fast. But one thing that's working with that made me realize after a long time, and I want to make this remark. I'm giving an example, but it happens with other quantities as well. So let's say we apply an electric field on the system, and this electric field will generate a current that will be flowing on this system. And basically, this is the definition of the conductivity. The conductivity is defined as this linear coefficient between the current density and the applied electric field. To be more precise, actually, this is a tensor because I can apply an electric field in the x direction. This can generate currents also in the y direction or the z direction. Of course, you have to be some specific material to give origin to that. But even to be more precise, I can write in a more familiar way, at least on this talk, which is basically I apply an electric field and I calculate or I look what happens with some quantity, some current J, current density, charge current density. And this here is some conductivity. And you can see that this is a response function. This is just the linear coefficient between the electric field and the J. This is a linear response, a green function or susceptibility. So the current operator, I can write in a simplified way like this. It's basically the charge times the velocity of the electron. And then I sum over all the electrons. Or in another way, instead of the velocity, I can write in terms of the momentum operator. And the thing is, when I apply an electric field, the momentum operator changes in this form, in a given gauge, doesn't matter, but it's proportional. There is a change which is proportional to the vector potential A. And this vector potential A gives the electric field, is related to the electric field that I'm applying. So for example, if I have an electric field which is E0 cosine of omega t, is a harmonic field just oscillating, then the A, the vector potential, will be just the integral of that. So this gives me 1 over omega E0 sine of omega t. So the vector potential is proportional to the electric field. So the change in the momentum operator is also linear in the electric field. So this means that my current operator, when I apply an electric field, this current operator is not only this, it's this one plus the change, this change coming from A, from the vector potential, which again is proportional to the electric field here. I have these two terms which are known as paramagnetic current or paramagnetic term and diamagnetic term. Diamagnetic current. This diamagnetic current comes from this term, which has a minus sign. And the operator that we are calculating, in this case, the expectation value, it depends explicitly on the external field. So if we want now to calculate the expectation value of the current, we have these two terms. And we want to calculate, again, let's use what we learned, the linear response theory. Our interaction with the external electric field can be written like this, with a scalar potential. This is more or less, I would say, the more usual way of writing an electric field. But there is a more convenient one, at least for this purpose here, which is coming back from our unperturbed Hamiltonian, which is basically the kinetic energy plus potential. And the P operator, when I apply the electric field, it will change to P minus EA. So my interaction will be just this, again in linear response, this will be just this term, which couples P with A here. And yeah, I can write this using the operator that I wrote before, the current density operator. So the interaction Hamiltonian is this one. And just to put this into perspective, like in the first equation that I wrote in the very beginning, that I'm applying an external electric field, or an external field in general. So here I have my external field in the form of a vector potential. This is a vector perturbation with 3 components, and this couples to the current density. And so my A operator, sorry, this is a bit confusing that I'm also using A, but the A operator that was in the very beginning is here, in this particular case, the current density operator. And I want to see what happens to the current density itself. So this would be a current response function that would be that would give the conductivity response. Okay, so in linear response theory, if we apply what we learned for this guy, the change in the diamagnetic term is proportional to the commutator of the operator itself that we are calculating, commutator with h int, which is also proportional. So this is proportional to the vector potential, this is proportional to the vector potential. So this term would be second order in the field. So this we have to throw off, because we already throw away many terms in second order, this should be gone. So the correct way of calculating this is the full current density is just the paramagnetic term calculated in linear response as I had before. This will be the Jp, which is not proportional to the electric field. It's just proportional to the H0 of the system. And H int, which is then proportional linearly to the electric field. So this term is linear with the vector potential A. And what shows up here, it's also the diamagnetic term, but not calculated in linear response as we had before. Just this is linear response, just an average with the unperturbed states. So this is known as the diamagnetic term that also shows up in the response. Yeah, and this also shows up, for example, if we calculate the torque, because the torque is proportional to L, the orbital angular momentum L, and L can be thought of as R vector P, and P again changes with the vector potential A. This is just an example, another example. Sorry. Okay, that was basically a remark, and now I will just show one more or less simple case where I actually started working with these linear response theory and green function susceptibilities. I basically started all my master degree a long time ago with this type of calculation, and I'm just considering a time-dependent magnetic field, B. When I apply magnetic field on the system, this couples to the spin density of the system, S, and we want to see what happens to the magnetization itself, to the spin density itself. And this, of course, will be a response which is the first S comes from the quantity I'm looking at, which is the spin density, and the second one is what is being coupled to the field, to the magnetic field, which is also an S. So this is the spin-spin response function. So we have a system, magnetic system, where I can have a static magnetic field just to define some equilibrium direction of this magnetization. Then this is my unperturbed system. I will apply then this B of t, which is a perturbation on this equilibrium. It's a transverse magnetic field, transverse to the equilibrium direction. This field will couple to the spin density or to the magnetic moment, and this will make this magnetization to precess. And of course, to be able to use linear response theory, I'm considering that this transverse field is much smaller than the static one. Otherwise, this would just give a huge response. This would not only precess, but could switch and do other things. Okay, and I will just consider this field as a precessing one, just a field that is rotating in the transverse direction of this. This is cosine of omega t along x, sine of omega t along y. This is just a field that is oscillating in this xy plane. When I substitute this guy here, I have cosine of xx because of this dot product, sine of sy, which I can rewrite in terms of the exponentials, and s plus and s minus. S plus is of course the usual one, sx plus isy, s minus is sx minus isy, just the ladder operators of plus one spin or minus one spin. Yeah, here. Okay, and now that I want the spin-spin response function, I will actually simplify this. We already know that we are dealing with spin-spin response functions. Instead of writing all the chi, s, the full operator, I will just use the simplified notation. I will just put the components that I'm looking at, s plus and s minus on top. And why am I using s plus and s minus? Because if I calculate the change in the s plus, which is a complex quantity, s plus is not a real number. There is a real and imaginary part, and these real and imaginary parts are related to the sx component and sy component. So with a single complex number, I have both components x and y. So this is convenient to work on with these plus and minus. But who is this guy? Who is the delta? What is the change? This means what is the change in this s plus operator, which you should have in mind that this represents the components in the Cartesian plane in xy components of this spin when I apply this field, this external perturbation. So we can go back to Kubo's formula and use this. We are applying a magnetic field that is coupling to the spin. A here will be the spin, and I'm looking at B, which is also the spin. But I'm not going to use this one. Actually, I'm going a bit further back, and I'm going to use this formula. Because we have the h int. I just wrote for you h int there, and I'm just going to bring back this formula, but now I'm just putting this, the B equals S plus, which is what I want to calculate. This is the same formula as I had before, just substituting B equals S plus. And now we have this H int here. When we substitute this guy, there are two terms, one which is S plus and another which is S minus. So the first one will give a chi plus plus response, which is written down here, is just a susceptibility, spin susceptibility plus plus. And here's the susceptibility chi plus minus, because plus comes from what I'm looking, minus comes from the coupling to the field in the Hamiltonian. Another interesting thing that I just forgot to say is that I'm applying a field. I mean, I'm theoretical here. I'm not an experimentalist. I know that this is impossible, but this field is only applied to a site 0. So this is a local field. Let's think that we have some probe that you are on top of a site 0, or this site 0 can also represent a cluster or whatever. But I'm calculating the response somewhere away, not at 0, but some place I. Not exactly the same 0. It can be 0, I equals 0. So I'm applying a field at 0 and looking what happens at 0. But I can also see what happens at some faraway place when I apply a field at 0. So this is chi I0 here because of that. Okay, this in principle will be a full response. But if I'm considering that my system is quite simple, my Hamiltonian is just kinetic term plus regular potential of the ions and so on, there's no spin-orbit coupling or anything, then this term here, this S plus plus, I can open up this commutator, I will have terms like that. And this term on this side, S plus applied to the ground state gives me a state with S plus 1 spins, because S plus is just the ladder operator that adds a spin to this state. However, on this side, S plus applied to the left side is basically having it's like S minus dagger. So S is this, all this term is S minus applied to this state and then getting the dagger. So this state just brings down the total spins on this by 1. And now I'm getting the projection of a state with S plus 1 spins into a state in a time later, time t. So this is at t equals 0. Then I project it in a state later with a spin which is S minus 1. If I have rotation symmetry on my system, if there is nothing that can bring down the spins with time, the spin from S plus 1 to S minus 1, then I cannot have this. This basically gives me 0. And this is what I'm assuming now, a very simple system that cannot have this. There's no spin-orbit coupling. So this is just go away because of rotational symmetry. This term vanishes. And I end up with only a very simple response, which gives me the spin disturbance, what is happening, what disturbs the system at a site I due to an oscillatory field at site 0. It's given by basically this quantity here. It's a very simple expression. I can also Fourier transform, and just to get rid of that, actually this, if I have a oscillatory field here, the response is actually, I can just do the Fourier transform of the susceptibility. So the response is still in time, but the susceptibility is the frequency dependent one here, because I'm applying an oscillatory field with one given frequency. So the response of the system will be also at that frequency omega. So I'm applying a field in a given frequency omega, the response of the system will be at that frequency omega. This is basically also intrinsic from linear response theory. You can only excite the same frequency that you're applying. And basically, that's actually a quite simple expression here. There are a lot of constants here. It's proportional to the external field that I'm applying, the amplitude of that field, some exponential because this is oscillatory, and then the dynamical transverse magnetic susceptibility. So this is dynamical because it's frequency dependent. It's transverse because it's the plus minus components, and it's magnetic because it's the spin-spin response. And this guy, it's a complex number. I can just write this as a absolute value of that times the exponential of some phase argument. So what does this mean? If we look at this expression here, we see that there is some oscillation. The exponential here is just plus 1, minus 1. It's just oscillating between plus 1 and minus 1. And the amplitude of oscillation, it's proportional to the field, to this field that I'm applying, because it's in response, but it's also proportional to this response function. So this guy gives the amplitude of precession in a site I, which again can be anything, can be 0, but can also be far away from that perturbation, when I apply a field at site 0. And when this is happening, when there is something happening at I, the site far away, this means that there are spin currents flowing on the system, because I'm not applying any electrical field or anything. The electrons are just on the system, delocalized, and when I apply a field, a magnetic field at site 0, and this is shaking this guy here, and far away this shakes, it's because the information is transported by spin currents. And I'll show an example soon. And then this phase argument is just the phase between the fields that I'm applying. Remember that the field that I'm applying is b e to the minus omega t, exponential of I omega t. But then here, the response of the spin at the site I, there is a dephase there. This phi term is just a phase difference. So one is precessing, the other is delayed far behind that. And if you remember, when I discussed fluctuation dissipation theorem, if I look now at I equals 0 at the place of the where the field is applied, the imaginary part of chi 0, 0 is related, gives me the excitation energies of that system, the intrinsic energies of that system. To give just again a very basic example, this is again how I started all my calculations on this topic. I can get, for example, a linear chain, semi-infinite linear chain, where I can calculate everything analytically. There are expressions for that, analytical expression for that. I can calculate this transverse magnetic susceptibility and as a function of the frequency. And here I'm calculating chi 0, 0 and getting the imaginary part. So these are the intrinsic energies of the system. And I see that I have these resonance peaks that depends on the field. If I apply a field which is 10 to minus 2, I have a large field with a resonance at low frequencies. If I increase the field, I push the resonance to higher frequencies. And this is basically the same picture that I showed before. This is actually from experiments, can measure this. It's just instead of measuring, in this case, I'm fixing the magnetic field and varying the frequency. And in this case, for example, from cavities, it's much easier to fix the frequency that is resonant to a given cavity and change the magnetic field that is applied. But both responses are related. Yeah, and this just shows that how this can be, it's not too complicated. But of course, we can do much more complex things. For example, this is just an example that I studied again many, many years ago, because this lecture was prepared many, many years ago. So we have, in this case, I had a graphene sheet with some magnetic impurities on that. And when I apply a magnetic field in one of them, the other one was also precessing far away. So the magnetic field is only applied at 0 here. And then I have some perturbation at some site far away. But then I can apply a gate voltage in between these. So this is completely spin independent voltage. It's just some gate voltage between these two units. And I can turn off the spin current that flows from this guy to that guy. So this will not feel the perturbation on this. So basically this could be one spin transistor where I can just put one a state on or off just by changing a gate voltage in the middle. And the information is transferred by spin current, pure spin currents. Yeah, so the spin current flow can be controlled by the gate voltage, electric gate voltage. This is another example, again from years ago, that I had now a carbon nanotube, again with two impurities, very, very far away. It's 60,000 units, atomic units, lattice parameters, one far from the other. But now instead of applying an oscillatory magnetic field, I apply a pulse. So this is the pulse that I apply on this green impurity here. So the pulse is centered at t equals 0. I apply this pulse here. And this is basically, now I'm calculating with the expression that I showed just before. I am integrating over frequency, of course. What is the change on the spin at a given site M, which is far away from this guy? So I apply a pulse on 0. The green curves, it's M equals 0. And the red curves, M equals these 60,000. And I see that as a function of time, I see a change, of course, when I apply a field in this guy, but then this dies away. The perturbation here dies away, and then this guy stops. But after a while, this guy starts to precess. With a smaller amplitude, of course, I'm also losing, emitting a spin current to the other side, and this nanotube is infinite. So I'm losing half of the current to the other side. And then this guy precesses after a while. And of course, this guy will also stop precessing and emit spin currents to both sides, which again reaches the first one, and so on. I have this moving to show what is going on. This is all using the calculation results. This guy precesses with the first one, the green curve, and then it stops. After a while, the second guy precesses and then stops. So this is just information being carried by pure spin currents on this system. And then after a while, this one precesses again with lower amplitude. And then after a while, this one will come back, and so on. Yeah. So just to finalize, I showed that an example with electric field. I apply an external electric field and see what happens to the charge current. This is the conductivity response. In linear response theory, this gives the conductivity. When I apply a magnetic field and look at the spin density, I have then the magnetic susceptibility. But I can also have mixed response. I can apply an electric field and see what happens to the spin density. Or I can apply a magnetic field and see what happens to the charge current. But of course, for this thing to be something to happen there, I need to have other special ingredients on the system. For example, spin-opt coupling that breaks rotational symmetry. For example, as I showed before, there was this chi++ susceptibility. These are very important for these mixed components. And of course, if for example, I'm applying an electric field or a magnetic field and see what happens to the charge current, or an electric field and see what happens to the spin density, or even if I apply an electric field and looking at the charge current, but when these mixed responses are not zero, when they are present in the system due to the spin-opt coupling, I can have, for example, magnetoresistance is happening on the system. For example, the charge current that flows from one direction in a given direction changes when I move my magnetic moment from one direction to the other. This is basically the definition of magnetoresistances, and we have studied the dynamics of that in this paper. And of course, we are not fixed to these quantities. We can look, actually, it would be also good to look at what happens in other quantities of the system to understand what is really going on there. We can have charge currents, but then if the electric field is causing some perturbation in the spin density, why is that happening? We can look at the torques, or we can look at the spin currents that directly, the spin currents that are flowing on the system. And yeah, like an example of these torques, we also looked at this recently. And in this case, there is also the remark that I made for the charge currents, where the operator is proportional to the field itself. It also happens here in the torques, and is actually, it must be taken into account. But on top of that, we can also look what happens in other, not spins and charge only, but also in the orbital angular momentum. These are all, when we have spin-opt coupling, these are all coupled, and this could actually be a mess. But not only a mess, it's also very, very interesting to see what's going on and to understand what happens in the system. Especially if you also consider that you have different kinds of materials. You can look what happens in metals, or in insulators, or in multi-layers, or in topological insulators. And all these material have their own properties and can be used together, maybe to give rise to some incredible new technology for the future. And hopefully you'll be one of them. So that's the end of my talk. Thank you very much for your attention, and I'm happy to answer any questions.
Okay, thanks very much, Filipe. So, any questions on Filipe's talk? Any question? I have one, a very simple question. Do you have in mind an example, a simple example where linear response would not be sufficient and where we would need to go to quadratic response?
Yes. Well, not only quadratic, but I can say where linear response fails. For example, if we want to investigate what happens, well, I'm talking about technology motivation, but in the end, if you want, for example, spin up represent a bit 0, spin down represent a bit 1, this means that you have to switch your magnetization from up to down, from 0 to 1. And this is totally nonlinear response. You want this to be your full response, and for that you need to really calculate the full dynamics of the system. But of course, what linear response gives you is that to take your system out of equilibrium, so your system is at equilibrium and you want to take it out, it's much easier to do at, for example, a given frequency. I showed some resonance before. So if you apply a field at that frequency, you will much easier take your system out of equilibrium than if you are off resonance, for example. Okay. So linear response gives you some idea, but of course, if you really want the full dynamics of not only switching, but anything, then linear response will certainly fail.
Okay, thank you. Yes, come please, Jawei.
I also have a very simple question that from what I learned, from the textbook is that when you applied an electromagnetic field, and then you can get 4 linear response functions: the density, the density current, the current density, and the current response function. And in your talk, you defined some other, like the spin response function. And physically, I can understand it. But my question is that is this response function somehow can be expressed in terms of those? Those 4. The density, current, and the density, current response functions.
Mm-hmm.
Yeah.
Yeah, that's actually a very good question. The way, when you write, let me go back to, for example, here, this general form. So here we have these operators that are coupled, one operator coupled to the field, the other operator coupled to this quantity that you're looking at. What can happen is that when you are calculating one of the functions, actually, let me show it. This is actually shown in the example that I mentioned, equation of motion here. Here, exactly. You can even see this happening here. So when I calculate the equation of motion of one ring function, in this case d dagger, you see that shows up another equation of motion, another susceptibility, sorry, which is the c d dagger. And then to calculate this guy, I need to calculate this one. And so I have to write the equation of motion for this one, the c d dagger. And then it maybe couples to another one and to another one. And then you have basically a system of equations to solve. And these quantities are, when you solve one, you basically are solving the full system, and then you have all of them. And why do I'm saying this? Because when I did this for the spin susceptibility, for the simple case that I showed here, the simple case, only the chi plus minus matter, and when I calculate the equation of motion of chi plus minus, that close up without spin-out coupling, and that's it. That's the whole story. But now, if I put spin-orbed coupling present, this is not zero anymore, and there are extra terms on chi plus minus that couples this one with that one, with chi minus plus, with chi minus minus. So actually, you can write this in a very general form, which is basically set of operators, and from these operators you can extract any quantity that you want of those that I wrote at the end. You can write, for example, the charge density, the charge current, the spin density, all of that. Only you need just to, of course, get the correct components, multiply, for example, by the Pauli matrix, or if you want the spin, or if you want the L operator, you just put the L operator in the middle, and so on.
Okay, thank you.
I hope that answers your question.
Thank you.
We can have time for a last question, if any.
Can I ask one question?
Yes.
If I'm on. Can you go back to 46 slide? I think 46.
This one?
Next one, 47, I think, yes. Yeah, 47. 40, no, the previous one. The green nanotube when you were showing it.
Which one?
This one, yes, 46. Okay, so here I have a question that when you see that the information is traveling through pure spin current, so it has a dying nature, right? I mean, after a particular time, the information, I mean, when you transfer from one spin to the other, and you see that again, the first spin is getting, I think it starts vibrating. So the same information is coming back. Is it to and fro or no?
I'm not sure if I fully understood the question. So one thing is that I didn't mention, but I don't have any type of dissipation here. For example, spin-orbed coupling or phonos or anything. This is again a very simple system, but still you see that it's still quite interesting. So what happens is that the spin current, I'm applying a perturbation on this spin, and the spin current is then emitted out of that guy. So the only source of real dissipation that I have is because this nanotube is actually infinite. So the spin current that is flowing to the left from this guy just goes forever away and never turns back. But then the one which goes to the right will reach this point, and then it will be absorbed. At least a part of it will be absorbed, and it will put this to process.
Okay.
And then the same thing will happen. But in between, there's nothing that dissipates energy or spin current or anything. The spin current just flows, and we also look directly at the spin current on this system, and we see that it basically flows infinitely without decaying.
Okay, so there is no decay. That means, okay. Okay, thank you.
Yeah, the only decay here is coming from these pieces that are lost. If I had, for example, a finite nanotube on both sides, it would be forever emitting one and the other.
Okay, thank you.
Okay, thanks again, Filipe.
Thank you.